All right, thank you for this opportunity to talk. I've been a staff scientist at NREL for the last 10 years or so, and before that I was at NREL as a graduate student, and then I moved to Berkeley for a brief while. So I've been involved in photovoltaics research at NREL for about 15 years altogether, including graduate school and a staff scientist position. And so oftentimes I think of what would it take to revolutionize photovoltaics. And so today I'm going to talk a little bit about some of those thoughts and how I think that perovskites and nanocrystals can play a role in this field. So I assume you can see my screen and you can see my pointer as well. Is that correct? No? Yes? Anyway, I'll continue.
Yes, we can see your pointer moving.
Excellent. Okay. So if we look at the photovoltaic capacity, the installed capacity as a function of time, you could see this increasing amount of capacity of essentially all the photovoltaic arrays in operation producing power and the amount of power that they can produce. And so if we look at this growing, we could envision that sometime around 2025 we would have essentially about a terawatt of installed capacity. And if you look at these dark purple lines, they indicate the annual amount of capacity that is being installed. And you'll see somewhere around now we're producing something like 85 or so gigawatts per year. For some reason, this number isn't really projected to increase very much in the next few years. But one thing you'll notice is that the increasing amount is still only near 1 terawatt. So if we think about how much electricity do we actually need, if you look at what the solar portion of the pie is, these numbers may be a little bit old, but nonetheless, the argument still holds that solar is about 2% of the renewable energy slice, which is about 9% of the total world energy consumption. And so if you look at the annual world energy consumption, this number is now approaching 20 terawatts. Certainly it's on the rise, and photovoltaics currently plays a very small portion of this. So there's plenty of room for more PV. You can envision having PV everywhere to where we would have essentially free electricity. Once it's all installed, it could continue to produce energy at a very low cost. So there's no reason to stop this production at its current stages. So if we were to think about how long it would take to generate enough photovoltaics to produce 20 or 30 terawatts of power, we're looking at something like 400 years at the current rates. So that shows that there is potential and a need for a revolution in photovoltaics. And so what would it really take to revolutionize photovoltaics? Well, I think what I'll point to is a combination of, number one, lower cost per watt compared to incumbent technologies, and number two, equivalent stability with silicon, which is the majority of the photovoltaic industry at this stage. Another revolution, or another way to think about this, would be is if we integrated photovoltaics into our everyday life. Everything we do, every product that we have has its own little power source. That would be another revolution, or another branch of this revolution to happen. And so these new technologies that we envision and play around with in the lab could contribute to this aspect of life as well. So the grand vision is, rather than 400 years, we think that we need to have a technology that can be manufactured more quickly. And so as a college student, I used to work at a newspaper, and one comparison that I made was that we had a deadline of 1 a.m. in the morning to have the final paper designed so that it could go to press, and bundles of newspaper would come back at 4 o'clock in the morning and go out for delivery. That gave them essentially 3 hours to produce all the newspapers needed for that particular application. And so if we think about that, and there are newspaper plants in existence now, maybe newspaper is a failing industry and we want to upcycle these newspaper plants and change them into a different technology. If we could produce photovoltaics with the same speed at which something like the New York Times press is run with one newspaper plant, you could produce essentially a terawatt a year compared to our 70 gigawatts. So a factor of 10 improvement with just one newspaper plant at that rate. So you could envision that industry taking off, and we would have a technology, if we could do this, if we could print solar as fast as we could print a newspaper, this would be a technology that we could really put a big dent in the amount of power that we need as a world. I also want to mention that there's some important new markets for photovoltaics, and perovskites can play a unique role in some of these as well. There's a lot of work on building integrated PV. If you're standing in a white room with white walls, you can imagine that's almost essentially the same as being inside an integrating sphere. So if you had one panel of that building in that room where the solar cell encompassed like essentially one wall and cost as little as the paint and the drywall that exists in that place, then you could recuperate some of those reflected photons, make your building more efficient. You could essentially put photovoltaics into the windows. Some technology developed by Lance Wheeler at NREL is shown here on this top right picture, where half of this piece of glass has a perovskite on it, and the other half of the piece of glass has that perovskite tinted into a black phase, whereas one portion of it is tinted into a clear phase. And so you can make these solar cells that essentially, and this works as a solar cell, so you can make these windows that essentially change like electrochromics, but when they're in the dark state, they actually produce electricity. So this is a new market that buildings could look into and would have a totally different cost structure as utility grade commercial PV. There's a lot of application for wearable PV. You can imagine disaster relief, where if you could print PV very fast, you could go to a place after some disaster strikes and be able to restore power just by essentially printing out photovoltaic modules and connecting them to some sort of grid and restoring power, and they wouldn't have to last for 30 years if they were cheap enough, and they could be produced on site. There's a lot of applications for space and aerial technologies, where certain companies sell photovoltaic modules at something like $10 a watt, which is 10 times the cost that is often thought of needed for utility scale photovoltaics. And there are products that actually can sell at 10 times that cost for specific applications. And so, if new technologies could come in and be more integratable in this fashion, there are other markets that new technologies could join. So previously I mentioned that there are sort of two criteria. One is lower cost per watt. If we look at how perovskites compare to cadmium telluride, this is an NREL analysis performed back in 2015, so it's a little bit dated. But if you look at the state-of-the-art, cheapest technology of photovoltaics at that time, which was cadmium telluride, and compare an equivalent efficiency perovskite, hypothetical perovskite module, and you would see that the cost savings is about a quarter, 25% cheaper than cadmium telluride. And that cost reduction comes in a lot of different components. It comes into cheaper capital expenditures of equipment to manufacture the devices, cheaper materials, maybe some less labor. But again, this is all hypothetical. This is a known technology where we know exactly how to produce it. We know the equipment that's needed, and the perovskites are still a little bit unknown. But from a cost perspective, it certainly could be lower cost at the same efficiency. At NREL, we do have some efforts on that. This is some work by Michael Van Hest's group and Kai Zhu's group, where we've basically cast perovskites on a roll-to-roll flexible glass architecture. You can spray these, you can print them. This particular example took only one 20 mil vial to coat that entire piece of glass that you can see there, which is like 20 meters long and 1 foot wide. And so it takes very little materials to produce such a thin coating like that. So it can be almost fully roll-to-roll coated, including all the contact layers, which is amenable to fast processing. Currently, the record efficiency is around 23%. There's always improvements in the record efficiency, and there's also possibilities to make multi-junction devices which could be more efficient. So this technology is low cost, and some of the topics I'll talk about today are the defect tolerance that is imparted from the perovskite structure. People also mentioned that the perovskites are radiation hard, and so they can handle space applications. And one thing that makes them really amenable is that they can be coated on nearly any surface. So if there is a really cheap glass or a cheap product that wants to be coated with perovskites or coated with photovoltaics, perovskites could be a good solution for that. So in addition to the lower cost, another way to improve that cost per watt is to increase the number of watts that the module can produce. And so there are many different strategies to develop photovoltaics that can break this dotted line that I have shown on this chart here, which is the Shockley quasar limit of a single junction. And so if you had a single photovoltaic layer operating at the thermodynamic limit, the maximum efficiency that you could achieve in that case would be about 33%. Gallium arsenide, which is the best semiconductor we know of right now, comes in at about 29%. Silicon is about 26%. 26.7, I think, is the record for silicon now. And perovskite's the record about 23%. So in a single junction layer, we can't really envision breaking 30% with any new technology. So, these other strategies where nanotechnology can play a role, or the processability of perovskites can play a role, we could envision tandem junction solar cells or new technologies where you play fancy games with the photons, such as multiple exciton generation, where you can split one photon into two electrons, or up conversion, down conversion, or ultimately a hot carrier solar cell, which has a thermodynamic efficiency of about 67%. So that's the ultimate goal, but no one knows how to build a solar cell like that yet. The second criterion that I thought was needed for a revolution in photovoltaics is that in addition to that cost per watt, you need to have equivalent stability to silicon. So this is perovskite's Achilles heel. So the biggest challenge associated with this is that we need to identify the particular unstable part of a perovskite solar cell and fix it. It sounds easy if you state it like that, but it's not easy because there are so many convoluted parts of the perovskite solar cell that contribute to the instability that is seen at the lab scale level right now. So you have ion migration, there's lithium in a lot of the cells, there's A-site and X-site cations and anions that can move around, and then also there are metals that tend to iodize in most solar cells. And so just the ion migration issue is really complex. There are photophysical processes that happen with moisture. So you'd have to essentially encapsulate the cell so you could understand that, or design the cell in a way to make it more robust so that it can tolerate that. And one of the things that makes perovskites so great is that they have a low formation energy for crystallization. But this also means that the material can disassociate with low energy. And so you have a low formation energy, but also a low dissociation energy for crystallization. So that's a challenge. How do we separate those two and retain the low formation energy, but essentially impede decrystallization? So we believe there's a constant need for studies that provide greater insight into degradation as a function of temperature and humidity, device configuration, all while tracking the output under standardized measurement conditions. So here on the right, I have just an example from a long time ago. This is a paper that was published in 2016, but in the perovskite world, that feels like forever ago. So if you look on the top, it's showing the relative humidity, and on the bottom, it's showing the normalized power conversion efficiency of solar cells that are being operated in various relative humidity conditions. And so you can see that as the humidity is higher, the cell degrades faster. And so this just highlights this point that the solar cells are unstable, that there could be chemistry solutions to this, and we can design perovskite crystals that would not be this dependent on the stability and as well as encapsulation strategies where you can overcome that by essentially encapsulating the moisture out. So at NREL we have a lot of these tools to study this degradation. These are tools that are built in a large part by Matt Reese, but other folks have had a hand in building these too. And so on the top left here I have what we call our Combi deg system, and so this just allows us to put a whole bunch of solar cells under constant operating conditions, and then we can scan them periodically, every so often, to understand how the different parameters of the solar cell are operating as a function of time. We also have chambers where we can eliminate the oxygen, eliminate the moisture, or we can intentionally introduce various amounts of stability. We could introduce ozone if you wanted to do that, or you could put them under any variety of atmosphere, and so we find that to be a really useful way to standardize and test these types of materials. And then the biggest challenge also is finding a light source that can remain on for hours and hours without the light bulb burning out. Solar simulator light bulbs are actually really expensive, so we have some approaches that mimic what you would get from a class AAA solar simulator, but they're much more lower cost. And then we had to design systems to make that light very uniform across these big solar cell arrays so that these small devices are actually being operated under the same operating conditions. So in our best case, we've developed a cell that without encapsulation, our role is that if we feel like we can make it more robust without encapsulation, we would be able to then use cheaper encapsulation methods, or ultimately have a solar cell that doesn't rely on encapsulation at all. But anyway, making it more hard to moisture and additional artifacts like that without encapsulation is a good goal. And so we've developed a cell that can last for 1,000 hours at max power point and retain about 93% of its starting efficiency. But this isn't good enough. So this is a solar cell that is under accelerated degradation testing because the light never turns off in this case. But it also needs to be able to handle higher humidity and needs to be able to handle obviously longer lifetime, elevated temperatures, and anything else that in an environment would do to stress such a device. So we've sort of taken a scan of the best papers in literature which highlight unencapsulated long-term stability and plotted them on this chart. And what we can see is that it's very difficult to parse out what one group is doing compared to another. So, one solar cell structure may be totally different. One may have an additive in the perovskite crystal itself or different contact layers or so forth. And if you really wanted to get a good handle on how these devices all compare, you would plot them on a plot like this and just look at how long it takes for them to degrade. But waiting 1,000 hours requires, waiting essentially a month in the lab, and that means for really slow turnaround time. And additionally, if you look into a lot of these papers, what you'll find is their atmosphere and their processing conditions are different. So in one case, it's under air, 40 to 50% relative humidity with a temperature range of 150 to 60 degrees. Or in another case, you have a solar cell where it's implied that the solar cell is the most stable alternative, but this one is measured at max power point in nitrogen at 85 C. And so comparing these is actually really challenging. So we just believe that there needs to be better standards for different levels of this. There's material levels where you're just trying to understand the crystallization and decrystallization, and then there's cell level measurements where you just want to understand how long the solar cell lasts. You don't really care if the perovskite changes in some subtle way, or if a contact layer interface barrier changes in some subtle way, but it doesn't affect the device performance. And then there's ultimately going to be module tests where these modules need to withstand different types of procedures such as temperature cycling and dark light periods and radiation effects and all these sorts of things. So I just want to highlight that essentially all of this is at the cell level up to now. All these studies that have been shown and are shown on this graph here are all still really small cell level measurements, and so we envision that there's another huge challenge of imparting these same types of studies on the module. So we made a small, what we call a mini module. In this, you can see these small scribe lines, which indicate the different cells, and these are all connected in series. And so in order to do this, this is how typical thin film solar cells are made into modules. In order to do this, you essentially need to cut through the perovskite. And so if you look at this cross-sectional image of the procedure that's needed to do this, the first cut, which we call P1, essentially cuts through the TCO on the glass, the ITO. So this basically breaks apart the two bottom contacts. That's not so challenging. The second one is a cut through the perovskite layer. This happens to the right side of P1, and this basically cuts through all the layers so that the metal from one cell can touch the ITO of the next cell over to essentially connect them in series. And then you have to cut through the whole perovskite layer again. This is called P3, this cut here. And that cut basically exposes perovskite to the ambient. And so that's just, so if you imagine a solar cell that is built up in a structure the way that we're used to building them, the top contact provides some sort of encapsulation layer to essentially block out interaction with the environment. But when you turn them into a module, you need to do these cuts, and these cuts can expose surfaces so that perovskite material can then be re-exposed. So, when we make a module like this, what we find is that it degrades much faster because of these interconnects. And so that's certainly a challenge that we envision perovskites are going to have as this technology becomes a little bit more mature. All right, so thinking about where perovskites are going to go and how they're going to enter the marketplace, there's a lot of groups that are working on different cell designs, and so I'm excited to see which one of these types of designs is going to be the first one to make it into market, and also which one may be the one that survives and lasts the longest and actually has a component towards photovoltaic production. One of the things I mentioned earlier is that they can be coated on nearly any surface, so you can imagine flexible modules. That has a totally different market than typical utility-grade modules that can be rigid. You can imagine semi-transparent modules as well. And then there's also companies that are depositing perovskites on top of silicon and making tandem junction solar cells. So, it'll be interesting to see if this technology first makes it into the market as a single junction technology, or if a tandem technology is the lowest barrier to entry to the market. So I'm particularly fascinated with this design. This is a company in China that's called Wonder Solar, and they have 110 meter squared perovskite array on their roof, and these are made in a very different way than traditional perovskite solar cells are. So essentially, they're all screen printed with a carbon back contact, so there's no metals in this device. And then the perovskite is infiltrated through the porous structure as a last step. So essentially, they can build the whole device, and then they just essentially soak in the perovskite layer, and it goes into the whole cell, and the efficiency is much lower. I think the maximum efficiency they've been able to attain is about a 15%, and these devices are operating around 10%. These are large modules here, with respectable efficiency, but certainly not enough efficiency to really overtake something else. But they have been in operation for nearly 2 years, or a little over 2 years, and I'm not really sure what their status is now, but I think that's a really important first step that is seen in commercializing perovskite solar cells. So a lot of my group's work is on nanocrystals in addition to these thin film perovskites that I've been talking about so far. So now I want to spend a little bit of time talking about how I envision perovskite nanocrystals could make or could play a role, or essentially how the nanocrystals are different than thin film perovskite materials that you may have heard a lot about. So essentially, if we just look at the differences, perovskite thin film materials are essentially solvated perovskite precursor with a low formation energy. These are molecules that are solubilized in a solvent, and so you can see on this picture on the left, the liquid appears yellow, and so then you essentially cast this across the substrate, and then as the solvent dries, the perovskite crystallizes out of that solvent, and you're left with a really nice, dense, large grain structure of perovskite materials. But that indicates that there's going to be a lot of surface solvent interactions, and there's a lot that's associated with that crystallization process. And transforming that up to a really large scale with rapid manufacturability may be a challenge. Right now we do a lot of devices by spin coating. There certainly are companies that have figured out how to do spray coating, and there's also large roll-to-roll processes as well. But that substrate solvent interface is going to be a challenge that I see that technology will struggle with a little bit. Perovskite nanocrystals, on the other hand, are essentially crystallized fully in the solution. And so here you have the perovskites in the right structure, and they're just in a solvent to essentially keep them separated, and then you can spray them or cast them onto a substrate. And then so you have a different challenge here. You have the assembly of these little blocks as opposed to the full crystallization of the perovskite material. So our devices made from nanocrystals are very similar in structure to these thin film perovskites, except for the active layer is essentially made up of these little cubes that are about 12 nanometers on a side, and they're just assembled between the contacts. And we've done a lot of work to understand how to get electrons to flow through that array, and they have some pretty unique properties. So the question is, how has the semiconductor system escaped us for so long? People have been working on photovoltaics for now about 60 years or so, and it's only very recently in the last 8 years that people have really considered a perovskite material as a photovoltaic absorber material, and that really came because all of the materials that have been analyzed in the past have either been all organic or all inorganic. And so if you look at the perovskite structure, the lead iodide plays a really important role. The lead iodide actually oriented in this perfect structure where you have corner sharing octahedra. That's what plays the biggest role in the perovskite optoelectronic properties. And so if you limit yourself to lead iodide and you look at the A-site cations that allow it to form into this perovskite crystal phase, essentially what you see is in this chart here, this is the Goldschmidt tolerance factor, which is just a geometric constraint that shows which phase this material system will form in for a given A-site radius. And so this is the A-site cation radius size. And you see that when the material is in this middle purple region, you have this nice perovskite corner sharing phase. If you have a very large A-site cation, it turns into a hexagonal phase. This is essentially a yellow phase. Optoelectronic properties are pretty poor in that phase. Also, if you have a really small A-site cation like ammonia or cesium, the material tends to want to be in this edge-sharing orthorhombic phase. And again, that doesn't have the same optoelectronic properties as the perovskite phase. And so if you look at what is in between those two phases, there's very few A-site cations to stabilize the perovskite in that right phase. And so methyl ammonium, which does happen to fall right in the middle, is really the ideal case for this. And so it's this interplay between having an organic A-site cation, which is methyl ammonium, and then an inorganic anion, which is lead iodide in this case, that I think has really let this material sort of escape from the global idea of what a good semiconductor should be. But now that we know that methyl ammonium lead triiodide forms, it forms into the right phase. It may not be the most stable material, but now that we know the optoelectronic properties are so good for that material, we can look at ways where you could look at materials that are on the boundary, like cesium lead iodide, on this case, falls right at the boundary of the perovskite and the orthorhombic edge sharing phase, where there might be ways to promote better stability into the perovskite phase with that. And so that's one of the things that nanocrystals do quite well, as I'll show. So if you look at the tolerance factor of cesium lead iodide, the temperature so on this plot here, above the dot, the temperature is basically the transition point. It's just a phase diagram where above the dot you're in the cubic crystal perovskite phase, and below that you're in the orthorhombic phase. And so if you look at as a function of the anion, which is either iodide, bromide, or chloride, you can see that this temperature drops down quite significantly, much closer towards room temperature. But for cesium lead iodide, which has the lowest band gap, you have a trade-off where you're increasing that crystallization temperature for the advantageous optoelectronic properties, namely the band gap. So if we look at cesium lead iodide, that phase transition temperature occurs at like 300 C. So if you really wanted to make a solar cell out of cesium lead iodide, just because that's an all-inorganic material, it's going to be nice and stable. You're not going to have volatile A-site cations in that case. You would need to essentially operate it above 330 degrees all the time, which is totally unfeasible. And so nanocrystals really caught my attention because even at room temperature, they're typically always in the perovskite phase, and they have really good optoelectronic properties. And so, looking at this system, I was really impressed by this work from Maxim Kovalenko's group in 2015, where they figured out a synthetic prep to make nanocrystals of the cesium lead halides across the whole spectrum from iodide to chloride, and they could tune the emission properties just by either changing the quantum dot size. So in this case here, the cesium lead iodide is shown for 3 different sizes, and that offers some degree of tunability, or you can essentially just substitute in different anions, and that gives you a different region of the spectral component, or you could just essentially use cesium lead chloride, which is on the blue end. And so I was most interested in photovoltaics, and so proper band gap for that is much lower than a lot of these materials. So certainly I'm interested in the lowest band gap that you can get here. And so this is with pure cesium lead iodide with the largest size. So we essentially just wanted to know a little bit more about this crystallization effect that's seen at the nanoscale. So as I mentioned, 330 was the phase transition temperature for thin films. But if you make nanocrystals, they stay in the cubic perovskite phase for a very long period of time in solution. And so this just shows an X-ray diffraction spectra for day 1 and day 60, where we show that we can keep them in the right perovskite phase. And then on the right is a TEM image that essentially shows the nanocrystals and how they might pack together. They're roughly 10 to 15 nanometers on an edge length, and they're always cubic. And the spacing between these is just made up by the organic ligands that are used to synthesize the materials, to basically crystallize them, and to keep them in solution. And so that's something that we had to overcome in order to make electronic devices out of these. But I'll talk about that in just a second. So first I want to understand a little bit more about this crystallization, this difference. So the difference between the bulk large grain material that tends to want to relax into the orthorhombic phase and these perovskite phase nanocrystals. And so the bulk lattice parameter is 6.28 angstroms, but that has to be measured at 300 C because at room temperature, as I mentioned, this material isn't in that perovskite phase. And so if you heat the material up over 600 degrees K, you can get it in that perovskite phase and measure its properties. And so as you cool that down, you would imagine that lattice constant would decrease a little bit, and we see that for sure. So if we look at a large nanocrystal, 15.5 nanometers in size, and we look at our X-ray diffraction and fit that to the Rietveld refinement, we can get the lattice parameter out of 6.189. And what we find is that as we make the nanocrystals smaller, so this shows the difference between an 8 nanometer, a 9 nanometer, and a 15 nanometer nanocrystal array, that the lattice constant shows some deviation as well. So the smaller the nanocrystals are, the larger the lattice constant is. And so you can think of this just like heating up the crystal. As you heat things up, they expand. When they expand, the lattice is then wide enough that a smaller cation promotes it to be in the perovskite phase. So the same thing occurs as the nanocrystal is made smaller. Basically what you have is, if you look at my little diagram here, this just shows the octahedra separated by these A-site cations. So you can imagine that if you only had a small nanocrystal of this, you'd only have a finite number of repeating octahedra, and then at the surface, these octahedra would essentially be able to spread out a little bit, just because there's no more material right beyond that, so they can essentially just repulsion forces will allow them to expand a little bit. And so if that's the case, then the surface can impart some sort of strain on the nanocrystal, and so you could imagine that the surface would just allow those octahedra to spread out, and that spreading out is very similar to what would happen if you heated the material up. And so these nanocrystals show a decreasing lattice constant versus size, and this is also seen in other materials like barium titanate. So this is just a size-dependent material trait, and we can use this to basically stabilize all inorganic materials into the perovskite phase. So as I mentioned several times, the ligands between the nanocrystals and getting electronic flow in these nanocrystals is going to be a little bit of a challenge in making a device, because you want to have an array where light is absorbed in the nanocrystals, but then the electrons are free to be collected by the contacts in your device. And so we've worked for a long time on lead sulfide and lead selenide quantum dot solar cells. So we applied a lot of those same ideas to this system. And so essentially what we found was a way to remove the surface ligands to allow the nanocrystals to go closer together, but still preserve passivation effects that you get from the ligands, so you don't have dangling bonds or unhappy lead atoms at the surface that might act as a carrier trap. And so the approach that we've done, and the one that we've used, is to essentially spin coat the nanocrystals. So then you have this film of nanocrystals with these long ligands on them, essentially spontaneously organized, and then we soak that in methyl acetate. And the methyl acetate basically converts and turns an acetate in place of the oleic acid that's on the surface. They both have the same functionality. And so then we're left with nanocrystals with really short ligands on them, essentially only the binding group of these ligands and no carbon chain. And so then the nanocrystals are no longer soluble in the hexane solvent that we use for the nanocrystals. And so you can then coat another layer on top of it without worrying about redissolving the original nanocrystals, because they don't have any ligands anymore. And so you can repeat this process over and over again, assemble a film as thick as you need, really, to be able to make an appropriate solar cell that can absorb a lot of light. So then from that approach, we can make an array of nanocrystals with the contacts on them, and then essentially formulate a photovoltaic device. You can see in this cross-section what the device looks like. If you look real close at this SEM, you can see that it's made up of really small grains, again on the order of about 15 nanometers. And then we have a really nice smooth hole conducting layer called spiro-omitad on here, which is a very conventional perovskite hole transport layer, as well as metal on the top. And so right off the bat, we were able to get a 10% efficient device, which is really good considering all the challenges associated with transport and nanocrystal arrays. So we were really excited about this, but one of the things that excited me the most was that the voltage was so high. So with the perovskite nanocrystals, the band gap was around 1.7, and of that 1.7 potential, we were able to get 1.2 volts out. And so this, at the time was essentially the highest VOC that you could imagine of any material with a band gap less than 2 eV, especially those made from solution. So essentially higher than anything except for gallium indium phosphide, which has a VOC of about 1.4. So this was actually the highest efficiency all inorganic perovskite solar cell at the time that we made it. It just happened to be made from colloidal nanocrystals. And then in addition, since these materials are so good at optoelectronically, we could take that device and just apply voltage to the contacts, and we get really bright electroluminescence out of this. So this just shows the ability to take this device and turn it into an LED without optimizing anything. We haven't even changed the contact layers. This was actually the 10% solar cell operating with a forward bias of about 2 volts. just glowing bright red. So one of the things that makes the perovskites so much fun is that they're essentially a playground. You have all these different ions. You can substitute the different ions in. You can envision doping them. You can change the band gap. You can change the absorption properties, the lifetimes, and all these sorts of things. And so just understanding what could we do at this starting phase. You know, we have these nanocrystal solar cells that seem to work really well. What happens if we start to modify the composition and substitute different ions in? We could envision just coating the surface with different ions and improving the transport. And so, so there's this paper that came out by the Kovalenko group again that showed me something that I've never seen in any other nanocrystal system, that essentially if you take two nanocrystal solutions and mix them together, almost instantly within 2 minutes you get a single photoluminescence peak that shows that the ions have essentially traded places and reached equilibrium in the solution. So this indicates that these materials are actually really dynamic, they're really interacting in solution, and this could be used as an advantage to essentially tune the properties exactly how you wanted in unique ways that we've never seen before in other materials. Going back to this diagram that I showed here of all these different A-site cations with lead iodide, we wanted to know what would happen if we take these nanocrystals, make a film out of it, and we take that film and we essentially subject it to different methylammonium bromides or formamidinium iodides to manipulate the composition of the film as a post-treatment on the nanocrystal array. And so essentially we made a batch of devices where we used formamidinium iodide, methylammonium iodide, formamidinium bromide, methylammonium iodide, and cesium iodide. And what we found in this case was that compared to the control, all of these treatments improved the photovoltaic current generation without harming either the fill factor or the VOC. And so, so just understanding what is going on with the surface and ways that we can now deliberately passivate the surface for better transport properties was really interesting to us. So we did a lot of work trying to understand exactly what was happening in that case. We found out that the quantum dots remain quantum confined. The band gap was essentially unchanged. If you look at the EQE spectrum, we weren't doing a full-on ion exchange with bromide because the absorption onset was still at the same position. And when we used formamidinium iodide, we had the highest efficiency. And so formamidinium would lower the band gap. So again, if we look at the EQE spectrum, we could understand whether or not we've changed the composition of the quantum dots in this case. But what we found was that only the mobility was doubling, and none of the optoelectronic properties of the material were the same. And so through further analysis that I don't have time to go into right now, we just learned that we have essentially been able to coat the nanocrystals and do deliberate passivation after we've removed the ligands off the nanocrystals. And this promotes higher mobility in the quantum dot array and allowed us to improve our original 10% device up to now over 13%, which is the world record for a quantum dot solar cell over any quantum dot technology, any material composition. So some work that we did in collaboration with Mokshin, who is a student at UT Austin, and Brian Korgel's group. He was here for a couple summers, and he looked into this quite heavily. So if you think about the two nanocrystals and what might be in between them, we know all the ligands that are on the nanocrystals as they're synthesized. With this formamidinium iodide treatment, we've subjected the films to essentially different time scales of this treatment and just monitored the composition using TOF SIMS and photoluminescence and some other techniques, as well as just device performance. And what we found was that as the soak treatment is longer, you can see the cesium and the lead and the iodide values stay very similar through the thickness of the film. They essentially don't change until we go to really long soaks over 1.5 minutes, more aggressive soaks. But we just introduced this FA signal, and so this FA signal is essentially gone. After 3 seconds, it increases a little bit. 10 seconds, it increases more. 30 seconds, it increases more, and so forth. And so what we're finding is that basically just allows controllable tuning of the properties by removal of the residual ligands that are left until at some high aggressive treatment, we've caused the materials to merge together. And so now you can think of this in two cases. One where you have quantum dots and you keep them as quantum dots, or you could intentionally merge them together as bulk materials if you wanted with more aggressive treatments. But this didn't allow us to tune the composition so much as we envisioned with that, which I showed in that mixing example. And so, one of the things that is quite interesting with the nanocrystals that we were able to do is that we were able to tune the composition of the A site across the whole range. Essentially, if you look at mixed A site perovskite materials, sort of analogs to methyl ammonium, where you've replaced the methyl ammonium with cesium and formamidinium. People are really interested in these materials because they're much more stable than methyl ammonium. But if you look at the crystallization of this semiconductor, people talk about low cesium concentrations and then really nothing up to 100%. And so if you look at the crystallization dynamics of this, formamidinium lead iodide crystallizes at about 150 degrees. And as I mentioned, cesium lead iodide is about 330 degrees. But somewhere in this temperature range, the Fa molecules fall apart. And so you can't make a 90% Fa composition and crystallize it over 300 degrees, because somewhere around 250 degrees, the formamidinium decomposes, and so you only have the ability to essentially change the composition up to about 40 or 50% in thin film materials. However, nanocrystal materials, as I mentioned, you can essentially just mix them together, and so we have made cesium lead iodide nanocrystals and formamidinium lead iodide nanocrystals, put them in the same solution, and just heated them gently to about 70 degrees C and just let them stir for long periods of time. So these nanocrystals interact with each other. They bounce off. The ions are labile. They can go into the solution, interact with a different quantum dot, and over time what we find is that these two photoluminescence spectra merge into one photoluminescence spectra right in the center. And so we can create an alloy of cesium and formamidinium just by mixing the nanocrystals together, adding a little gentle heat, and letting them interact. And so we were able to do this across the whole range of the spectrum. Obviously, we can make the pure phases, but we can make 25, 50, and 75%, and we see a real linear shift in the X-ray diffraction that tells us that we're getting a nice alloying effect of the two. And we can measure the activation energy of cesium going into a formamidinium lead iodide quantum dot, or formamidinium going into a cesium lead iodide quantum dot. So we can measure those activation energies, and what we find is that they're about 2 times that of the activation energy associated with the halide mixing at about 67 MeV, or 670 MeV, sorry. So then we were able to make devices that span that whole range, where the composition can be 0% Fa, or 0% cesium, or 25, 50, 75, or 100% cesium in the dots. And then we could compare those to thin films of the same composition. And so, as I mentioned, in the thin film form, you can't really go much beyond about 30 or 40% formamidinium because of the temperature of the crystallization. But if we compare them on the same plot, and we just look at the VOC as a function of the band gap, first of all, we see that the perovskite quantum dots all produce a slightly higher voltage than that's produced in the thin film form, so this is really interesting to us. And secondly, we can look at the VOC as it's compared to the detail balance thermodynamic limit as a function of the band gap. And so if we look at the cesium lead iodide quantum dots, they provide us with the highest voltage of about 1.2. In this case, it looks like it was about 1.15 volts or so. But the theoretical limit in this case should be a little bit over 1.4. But as we add more formamidinium to the dots, we see that the overall voltage drops a little bit, but it's actually much closer to the thermodynamic limit. So if we plot these dots as a ratio of their thermodynamic limit, which we call the VOC divided by the maximum VOC for that given band gap, we could see that the formamidinium dots reach about 89% of their thermodynamic limit, which is really impressive for almost any photovoltaic technology. So, as I mentioned, there are quite a few opportunities for perovskite quantum dots. They have modified phase properties. They produce high all-inorganic perovskite PV devices. We have the ability to change the surface passivation structure, and so we can make these not necessarily all inorganic perovskites, but we could add organic components into it as we desire. We have a wider compositional tunability, as well as high VOCs compared to thin film versions of the same material. And so there's these additional opportunities as well. You can use more familiar traditional organic solvents such as hexane, octane, toluene, and chloroform. You can blend dopants or polymers or additives that are soluble in organic solvents rather than limiting yourself to the polar solvents that perovskite precursors are generally solubilized in. This also gets away from the idea that larger grains always equal better performance. In this case, we have really small grains and we have really good performance. So just understanding how the material crystallizes, how you passivate the surfaces, how you understand transport in the materials could be a way forward, and you could think that there might be unique ways to deposit these at very fast, large scales, as well as they offer great potential for dual-purpose devices, LEDs, solar cells in one, or emitters, display applications, or lasers, or other applications as well. So my final conclusions are that perovskites have the potential to revolutionize the PV industry and, in general, just the way we think about electricity. And I'm interested to see over the next 10 years or so how I think these materials might first make it into the marketplace, whether or not it's going to be a single junction PV technology. What would be the cell design? Might it be a silicon on perovskite or perovskite on silicon tandem? Might it be this case where the contacts are all deposited first and the perovskite is then infilled, if this technology could then bridge the gap from its current 15% efficiency to a more respectable over 20% efficiency? Or is it that these materials become integrated into buildings or applications that traditional PV can't do, where you could change the color from clear to a tinted product? Or maybe the first PV product isn't, or the first perovskite product isn't PV related at all. There is a company that has been making QLED TVs using perovskite quantum dots since they're such good narrow emitters, and so people can get really bright TVs out of these as well. So maybe the first perovskite product isn't even a photovoltaic. But anyway, so with that, I would like to thank all my colleagues at NREL and elsewhere that work with us on these materials. And NREL is actually collaborates with a lot of groups. We have some collaborations going on with UT with Brian Kogel's group right now, but there's also a lot of other interaction within the U.S. and internationally. And so I'd like to thank my funding agencies, which is Department of Energy, as well as some DoD work that we get funded to do this, as well as internal NREL funding on certain projects.
Great. Thank you so much, Dr. Luther. We really appreciate it. I'm sure that there might be a few questions. So if anyone has one, feel free to either type it into the chat window, or you can use your microphone as well. It looks like we've got one in the chat now, and I'll let you get to Oh, no problem. I can. That's okay. I can read it to you then. That might be a little bit easier. So, Dr. Korgel asks, what are your thoughts about the need for PB in the absorber layer in commercial products? PB as in boy. For lead in the absorber.
Is there a way I can look at that? Oh, you're asking. Oh yeah. Yeah. So, my thoughts are that it does have lead in it. That is something that a lot of people talk about as being a potential hurdle for this technology. But I think there's a lot of examples where existing technology is in place, maybe that outweighs the downside to having lead there. So, it's not cadmium, it's not arsenic. Those technologies get used, or those atoms get used quite a bit in other technologies. But yeah, certainly there's a lot of research on lead-free perovskites, but honestly, it's the lead iodide band structure that imparts the majority of the functionality in these materials, and so lead is a key component in these. So that's certainly something that needs to be hashed out at a more
We've got a question here at UT. I'll let him take over.
Hi, Dr. Luther. Thanks for giving the talk today. This is Tim from the Kogel Group. I was wondering, so in the bulk thin film community, there's a bunch of research going into, especially in the mixed halides, perovskites, photo-induced phase segregation, how people have noticed that for some reason there's this spontaneous phase segregation when you shine light onto perovskite thin films or when the thin films in devices. How do your nanocrystals, especially the mixed halide ones, which you just touched on briefly, compare with the bulk materials in that respect? And do you think that there's something special about using nanocrystals that would inhibit this photo-induced phase segregation?
Yeah, that's a great question, and I know both sides of the answer to that question. So there are papers that indicate that this phase segregation is actually suppressed in nanocrystals, and so you can envision that because they have these grain boundaries, the propensity for the different ions to separate is actually inhibited because of those grain boundaries. So you're going to keep your iodides and your bromides in a really close proximity. Another way to envision it could be more problematic, I don't think people have shown this yet, but the surfaces are actually quite dynamic, and so even in the film form, you have ions that could essentially, those grain boundaries could actually be channels for ions to move more so, and so you could promote even worse phase segregation in that case. And so I think that answer is totally up in the air right now. It's not known. People have argued that the phase segregation is actually suppressed in nanocrystals, but I could imagine there would be cases where it could actually be worse in nanocrystals. So I think right now just understanding how the grains work, understanding more about how to passivate on the grains to prevent that.
Yeah. Thanks. I have a quick follow-up. So you were talking about the dynamic grain boundaries. Do you think that ligand passivation of these grain boundaries, as you have in nanocrystal films, would sort of maybe help the inhibited argument? Like you would inhibit this photoinduced segregation more because of these ligands, or do you expect the ligands to maybe increase the degree of dynamic behavior of these surfaces?
Right. So I think from a wide-angle view, you can use the surfaces to block. I'm getting a lot of static on the phone here. But anyway, you could use those ligands to essentially block that segregation. But as that interacts with solvent or moisture or things in the air, you'd have to make sure that those ligands are bound really tightly to the nanocrystal surface. So I think it's certainly an opportunity. If you're looking for me to say, is this an opportunity to make a absorber layer where you don't have as much segregation?
All right, thank you very much. Very interesting answer.
But further research is needed to figure out exactly how to do that.
Okay. We'll just throw it out there one more time to see if there's any other questions. It doesn't look like there are just yet, but okay. Well, again, we just want to thank you, Dr. Luther, for taking the time to present this talk to us. We really appreciate it, and I know that here at our group, and we've had Mokshin there working with you a few summers, so there's a special interest for us. So again, we really appreciate it. Great. Well, so we'll have a recording of this talk up on our YouTube channel sometime shortly after this. On top of that, we've got a few other talks coming in the next month or two. We'll have a short break for the holidays, but then after that, Sarah Kurtz from INREL as well will be giving a talk on January 15th. And then we'll have Hunter McDaniel from Ubiquity, and Yoda Solar, and Varun Rai from UT Austin as well. So we've got some talks coming up in the future. So thank you again, Dr. Luther, and please keep an eye out on our site for additional talks going forward. Thank you, everyone, for joining us.